Let's begin. Hi everyone, I'm Min Yang from the Trusted Firmware AM team. Today I will give a presentation about Trusted Firmware AM implementation update of the FM new features based on FM 1.1 alpha version. First, let's see what's FM and TF-M. The FM PSA firmware framework for AM defines a standard programming environment and firmware interfaces for implementing and accessing security services inside the root of trust. The framework standardizes the secure root of trust service design and facilitates secure application development. The latest FF.M version is the Alpha extension. Trusted Firmware M is a reference implementation of FF.M spec. It is an open source project on trustedfirmware.org. FM spec is developed in conjunction with TF-M. Continuous feedback will drive the evolution of FM and TF-M. They provide a complete solution to cover performance, flexibility, security, and provide a configurable implementation to fulfill various requirements from resource-constrained devices to resource-rich devices. The update today will cover three aspects. The stateless root of trust service, which improves the efficiency of calling sessionless services. The secure function model, which improves the efficiency and the performance for function-based services. Many services do not need to maintain dedicated execution contexts and can be called via direct access. The IPC model may be a bit heavy for them. Features of FF.M spec can be configured flexibly. Customized configurations can be adopted to cover different kinds of requirements. Before the update begins, let's take a quick look of TF-M software architecture. Roots of trust services are encapsulated in partitions. A partition owns its code and the private data. It is a single thread of execution and the smallest unit of isolation. The black line in this picture is the isolation boundary. The boundary can be different under different isolation levels. The SPM, Secure Partition Manager, manages the partition threads and provides the interface for partitions to communicate. First, let's see the stateless root of trust service. In FF 1.0, services are session-based. The client always needs 3 steps to finish a service call: the PSA connect, PSA call, and PSA close. IPC messaging is based on a request and response model. During the session, the service needs to maintain the active session data and resources. But there are a lot of services that only provide standalone operations. For example, the PSA crypto API. For example, the PSA storage API. These services do not require any non-volatile state or sources to be maintained. In FF 1.1, such kinds of services can be stateless. Clients do not need to prepare connection or disconnection messages anymore, just a single PSA call to the service. No session data is maintained by the service. This mechanism can improve service efficiency by avoiding connection and disconnection message processing and decreasing the thread scheduling overhead. TF.M implements the stateless service feature by applying following items. Firstly, since a stateless service requires a stateless handle, TF.M includes and generates the stateless handle automatically. An indicator bit, the client version information, and handle index are passed from the manifest attributes and then encoded into the handle. The client version is required because SPM needs to check the version policy. Secondly, TF.M maintains a reference table for stateless services in SPM. The table is initialized at the service loading stage. While referencing a service from the table, the index in the status handle is used as the table index to find the correct status service. Thirdly, TF.M makes some changes to the existing PSA APIs. TF.M disables PSA connect, PSA close, and PSA set handle for the stateless service. And the handle feature in the message is also unavailable either, because the handle is used for recording the session state, and the stateless service do not have sessions. When a client uses the PSA call to request a stateless service, the handle passed into this API must be a stateless service handle. Some TF.M native services are already implemented as stateless. For example, the crypto, the internal trusted storage, the protect storage as initial attestation service. Let's see an example. Compared to FF 1.0, developers need to change 3 attributes from the manifest to create a stateless service. Developers, for example, we set the PSA framework version to 1.1, connection-based attribute to false, and the stateless handle attribute to auto. Then let a client call the PSA call with a service status handle. The target service will be called and will return success result. Next, another update is the secure function model. In IPC model, as the first proposed model in FF 1.0, is better isolation-oriented, but the thread management and the local I/O WAC buffer mechanism can be a burden on a simpler system. If services are relatively simple and quick, a function-based model is more straightforward for developers and can be well managed under isolation and security considerations. The FF.M model is applied for the above reasons. The model uses callback functions in root of trust services, which can lower the runtime cost. It uses the same client APIs as the IPC model, which makes it easy for developing and porting. The SFM model can also be combined with the IPC model. This makes the solution very flexible. This picture shows the SF1 rationale. In a simple SF1 model, SPM works under a library-like mechanism. Therefore, different from IPC scheduler, it is a function call when a client calls the PSA API into the SPM, and is also a function call when SPM calls the SF1 service. As an intermediary, SPM is responsible for managing context, store and restore in the calling process. SF1 model can work together with IPC model as an extension. IPC scheduler in SPM manages the IPC partitions, and SPM also manages the service function libraries for SF1. The red box on the left is the existing IPC model in TF-M. A client requests an IPC service by sending requests to SPM. Then the client is blocked and wait for response. IPC scheduler will schedule the running of all partitions. Only when the target service is scheduled will the request result return to the client. The red arrow in the picture is where scheduler happens. The black box on the right is the SF1 part. We assume that an IPC service needs another SF1 service. At this time, its role becomes a client. Since the target service is a SF1 service, the request to service is finished following a library-like mechanism. There's no thread scheduling happening in the flow. In IPC model, client and service have their private stack for isolation reasons, but SF1 partition can optionally enable private stack if isolation requirement satisfies. It depends on real application scenarios. Generic model of the two models are the same. Inside SPM, TF-M implemented three parts: the entry, the FM part, and the backend part. The entry checks the isolation requirements. If crossing boundary is required, it will use LVC call. Otherwise, it uses a plain function call to FM APIs. In IPC model or high-level SF1 model, crossing boundary is usually required. This part is specific to isolation, but not specific to models. The backend part, it checks the model. If the target service is an IPC service, the scheduler will be activated by the SPM. If the target service uses a SF1 model, the context will be managed by the SPM. The backend part is specific to models. Let's see an SF1 example. To create a SF1 partition and service, developers need to set 3 attributes for a specific SF1 partition. First, set the PSA framework version to 1.1. Set the model to SF1, which is different from the IPC model, and set the entry init function. These attributes can be optional. Then create secure functions. The input argument of the secure function must be a PSA message. This example SFN service simply receives a message and prints a string. TF.M provides configuration flexibility for different requirements. Developers can choose which features to use depending on system requirement. For example, some devices may have very limited performance and memory resources. The project on such devices should keep small and only have basic functionalities. Developers may use level 1 isolation, SFN model, stateless services, and MMLVec feature to save system resources to a maximum extent. On constrained device, developers can decide which features to adopt according to use cases. But SFN model and stateless services are always preferred because they can achieve better performance without influencing isolation requirement. If on a high security level with very rich resource device, developers can use all these advantageous features to achieve best security level and not influence the performance. This table shows some possible combinations. The final choices depends on developers and the real application scenarios. To sum up, the stateless services features has been supported since TF.M 1.3, and the SFN feature is under upstreaming stage. Please check review.trustedfirmware.org for updates. While implementation, one challenge is the configuration management. The goal is to provide a neat and easy configuration for various combinations. Another challenge is the context management scenarios. High isolation level SFN context management is still under estimation. Any feedback from you is welcome. You can contact us by subscribing TF.M mailing list and joining the TF.M tech forum and leaving your comments on the upstream patches. That's all. Thank you for listening.